Hello everyone. Our next topic in the lecture series of thermodynamics is Maxwell's relations. But before going into Maxwell's relations, we move on to lecture number 32. Just the previous lecture, Gibbs-Helmholtz equation. A little typographic error may be corrected here. This was slide number 1 in the previous lecture, and this was slide number 2. Okay, here it was written that in the slide number 2, by putting del G del Tp in place of del G del Tp. So this is a typographic error. So please make the correction. Here you put minus S. Just here in place of minus S you have to put del G del Tp. So the correction should be like this. Okay. So this is the correction. It is blinking. So let's move on to lecture number 33, which will be covering Maxwell's relations. Okay, so we have the fundamental equations of thermodynamics. We have in total 4 equations. Okay, and these equations are number 1 in terms of U, in terms of H, A and G. du equals to TdS minus PdV, dH equals to TdS plus VdP, dA equals to minus PdV minus STT, and dG equals to VdP minus STT. So these are equations A, B, C, D. Here we are writing them as equation number 1, 2, 3 and 4. And remember lecture number 3 of thermodynamics, where we discussed the cross derivative rule. And the cross derivative rule was, if Z is a state function or dZ is a perfect differential, so that its expression was like m dx plus n dy, then according to the cross derivative rule it can be written that del m by del y at constant x equals to del n by del x at constant y. So let's apply this cross derivative rule on these 4 equations, because all this u, h, a and g, all these 4 parameters are the state functions, and they have this type of expression, such as here m is t and n is minus b, here m is t, n is plus b, and so on. Whereas in place of dx we have ds, in place of dy we have dv. Okay, so from, if we try to obtain the cross derivative rule result from equation number 1, then it should produce the result del m del y x, isn't it? So m is t here, so it should be del t, then del v would go to the denominator and s should be kept constant. That must be equal to minus, due to this negative sign, that should be equal to del p by del s at constant v. So this is Maxwell equation, Maxwell relation number 1. Similarly here, from here, del m del y, that means del t by del p at constant s, must be equal to del v by del s at constant v. Here it will be both sides negative sign, so it will be a positive relationship. Both sides will have positive signs due to having negative signs in both sides. So it should be del p by del t at constant v must be equal to del s by del v at constant t. And finally here this relation should be negative relationship, and it should be del v by del t at constant p must be equal to minus del s by del p at constant t. So let's see the 4 relations. Here are the 4 relations. So just have a look on the cross derivative rule and try to apply them on this equation and try to find out all these 4 relationships. So these are the 4 Maxwell's relationships that which can be obtained directly by applying the cross derivative rule. But if you are asked to derive them directly without using the cross derivative rule, then what would you do? Okay, so let's derive the Maxwell's relations without using the cross derivative rule. So here, as for example, I will show only one example, and rest of the 3 you will do yourself. Okay, so suppose let's derive this one. Okay, so here you see that this is the actually equation number 4. Actually here it is equation number 8, this one. That means the 4th Maxwell relation, del v del Tp equals to minus del s del p t. Okay, this one. So this is equation number 8, or the fourth Maxwell's relation. So here one thing we have to keep in our mind, that here the variable parameters are T and P. Okay, with respect to temperature and pressure, the parameters are changing, and we know that G, that means Gibbs free energy, is a function of P and T. Similarly, you have to keep in your mind that A is a function of T and P, while H is a function of S and P, and finally U is a function of S and V. So you have to just have a look on this denominator parts. Okay, so these variable parts, if it is, again I repeat, if it is S and V, then it should come from the du relationship. If it is S and P, then it would come from the dH relationship. If it comes from the T and V, then it would come from the dA relationship, and if it comes from T and P, then it would come from dG relationship. So we have to start from the dG relationship. Okay, so here the two variables are P and T, with respect to which the state function that is changing is G. Therefore we have to start from G as a function of pressure and temperature. Okay, and dG has the expression like this. Okay, this is the total differential, del G del Pt dV plus del G del Tp dt. So this is equation number 9. And on the other hand, the fundamental equation. So what is the fundamental equation? dG equals to V dP minus S dt. Actually this is equation number 4. Here it has been rewritten as equation number 10 here. Okay, so we have to compare equation number 9 and 10. So in equation number 9, with dP we have del G del P T, and in equation number 10 we have V into dP. So actually this one equals to V. Similarly, this one is equal to minus S after having compared with equation number 10. So we can draw the conclusion as equation number 11 and 12. See, this is del G del Pt equals to V, and del G del Tp equals to minus S. Thus we get equation number 11 and 12. Now we have to differentiate both the equations. If it is differentiated again with respect to P, that means G is differentiated with respect to P at constant temperature, then you have to differentiate this with respect to T at constant pressure. Similarly, in case of equation 12, it is found that G is differentiated with respect to temperature at constant pressure. So next time you have to differentiate both sides of this equation with respect to pressure at constant temperature. Okay, so first of all we have to differentiate both sides of equation 11 with respect to temperature at constant pressure. What is the result? In the left hand side we'll get a double differentiation, del to G by del T by P, and in the right hand side differentiation of V with respect to T at constant P, so it is del V del T P. This way we get equation number 13. And similarly, in case of equation number 12, after having differentiated with respect to pressure at constant temperature, we get equation number 14, which has in its left hand side del to G del Pt del P del T, and in the right hand side it has minus del S del P T. Okay, so the left hand sides of equation 13 and 14 must be equal, because G is a state function. Therefore left hand sides of equation 13 and 14 are equal, that is these two are equal. Therefore definitely the right hand sides would also be equal, and the result is this one. This is the Maxwell's relation number 4. Okay, so this way you can derive all the 4 Maxwell's relations. So that's all, and here is the gist. Again I am showing you here by using U as a function of B and S, here by using H as a function of P and S, here A as a function of T and B, and this one G as a function of T and P, as it has been shown here. Okay, so that's all. Thank you. Have a nice day.